So you might ask the question, how did the Earth and Moon form like that? Why are the two things that are, you know, on a cosmological scale of things, roughly the same size, orbiting around each other? But there are some other facts that are interesting about the Earth and the Moon. Now, this is a beautiful picture, actually, I just wanted to show, taken from orbit around planet Mars by a space probe just a couple of years ago. So this is the view of the Earth and the Moon looking back from Mars. One of the very interesting things about the Moon is that it's got very little iron in its core. Now, the Earth, as we'll see a little bit later on, has got a lot of iron in its core, which is actually responsible for its magnetic field. The Moon seems to have very little compared to the other planets and many of the moons in the solar system. So that's a puzzle. If it formed in the same place as the Earth, then why has the Earth got a lot of iron in its core and the Moon has got very little? The other thing, and this is one of the big words that I want to use, but it's got a simple explanation, is there's a lot of spin in the Earth and the Moon system. The Moon is very big compared to the Earth. It orbits around the Moon very fast. The Earth spins and the Moon spins. And one of the fundamental principles of physics, one of the fundamental principles of science, is that spin, this thing called angular momentum, doesn't just get invented. It has to come from somewhere. So when you see something spinning very fast, like the Earth and the Moon system with the Moon flying around the Earth, you need an explanation for that. Why is there so much angular momentum? Why is there so much spin? We also went to the Moon, as I mentioned earlier, I think one of the greatest achievements in human history, back in 1969, when I was about 1 year old, actually, so a long time ago. But we went there, we got moon rocks, and we brought them back. We found that the composition of the moon rocks is very, very similar to the Earth. Right? So the rocks seem to have come from roughly the same source. But by looking at the way that little radioactive atoms, radioactive elements in the rocks decay, we can date them very accurately. And it looks like they're about 30 to 50 million years younger. Now that's not very much younger, because we know from dating the Earth and dating the whole formation of the solar system that the Earth was born about 4.5 billion years ago. So 30 to 50 million doesn't seem like much, but we can date rocks that accurately. So that seems to suggest the Moon was formed very slightly after the Earth. So we've got this picture and a bit of a puzzle. The Moon is a bit younger than the Earth. It's spinning very quickly. It's made of very closely the same stuff as the Earth, very similar stuff, but there's very little iron in it. So what's the explanation for that? Well, there is a theory which is pretty widely accepted, which explains all those things. Some people question the theory, and this is why I think it's a beautiful example of the way you do science, because it's not 100% correct, it's not 100% accepted, but it works. And it's beautifully illustrated by this beautiful picture, actually. What we think happened is that very early on in the formation of the solar system, so let's say 50 million years after the Earth formed, there was another planet very close to the Earth, about the size of Mars. And the theory goes that this planet hit the Earth in a glancing blow. Now think what that would do. So you hit the Earth in a glancing blow. You knock off loads of bits of the Earth, but not the centre of the Earth. Now when planets form, the heavy things drift towards the centre of the planet, and that's why all the iron, or most of the iron in the Earth, sits at its core. There would have been enough time for that to happen, and so when this collision happened, the bits that got knocked off were not very rich in iron, because all the iron was sat at the middle of the Earth. That then knocks loads of bits off. Also, because it was a glancing blow, it puts loads of spin into the system. It's just like kicking a football at the edge, and it spins and curves. Right? You smash something across the edge of the Earth and you put a lot of spin in, which accounts for the spin. It also accounts for why the rocks seem to be the same, because the Moon is indeed made of bits of the Earth, so the same isotope contents. And because it happened 50 million years after the Earth formed, it explains why the radioactive clocks on the Moon are a little bit younger. So I think that's a beautiful example of a theory. It seems that the Moon indeed did form in a planetary collision about 50 million years after the Earth was formed.
There's always going to be people who don't like what you do, don't know how you do.
Yes.
But what's surprising for me, and actually I find, increasingly I'm sort of, defending you and science communication. Particle physicists say, oh, you know, Brian's gone off, he's doing astronomy now, and, you know, when was the last time he did an experiment at CERN? Astronomers say, oh, you know, Britain's favourite astronomer, he's not an astronomer. And then you know, there's the people who say, oh, you know, you're dumbing down science, the background music's too bloody loud, you know. You know, how do you cope with this? Are you able to sort of compartmentalize?
Yeah, I mean, the first thing to say is that you hear very little criticism from the top level. So from the top people in universities, people at the Royal Society also fund me, and those people, because I think at a high level there's a clear acceptance and view. Acceptance is the wrong word. It's kind of it's known that science has to be in the public arena, of course, because it's primarily publicly funded. So that's one thing. We know that we need more school kids to want to come into science. The government defined it as strategically important. Physics as a strategically important subject. So we know that the economy is based on that flow of scientists to a large extent, actually. I mean, the figures are of order over 40% of the economy is what's defined as knowledge-intensive services and industry. So that's really, the university system lies at the foundation of that. So therefore, it has to be part of culture, part of popular culture, has to be celebrated, accepted, and has to be something that children particularly, but parents as well and taxpayers want to support and want to do. So that's well accepted at the higher level. You get, you know, and I don't see much criticism actually. I mean, you might say, you know, the occasional bits and bobs, but actually, you know, when I get invited to the big astronomy conferences, the obviously particle physics, and in general, I don't see it very much. I think it can be overstated, that. Yeah, I think the world, I mean, I don't know what you think, but I think the world's moved on, actually. I know that I got quite friendly with Carl Sagan's widow, Andrianne, who co-wrote Cosmos, a remarkable woman. And she has told me, you know, Carl Sagan used to get unimaginable criticism. You know, he was famously wasn't allowed into the National Academy of Sciences. He was blackballed from the National Academy of Sciences because he was popularising science. One of probably the greatest science populariser, arguably, that's ever lived. Right? And so that doesn't happen anymore. You don't see. Actually, funnily enough, but I think it's quite good actually. The most criticism, if I ever see criticism, it actually tends to be from physics students. It's quite funny if you look on the web. You know, you get these people. He doesn't know what he's talking about. And I actually quite like that because actually, you know, you're supposed to be pure and rebellious. I was, right. It's just if physicists are supposed to be like physics. That's it. I'm going to be a physicist. So I even quite like that. I look at them and go, oh, yeah.
You're blessed.
1 million particles per second fly off the sun, and that's called the solar wind. Another way of looking at that is it's 7 billion tons of sun every hour get lost into space. That's an incredibly violent wind of particles flying our way. Many of those, some of those, hit the Earth. And what we know is that if the Earth wasn't protected from that solar wind, then its atmosphere would most likely have been blown off into space long ago, and we wouldn't exist. So what is the explanation for why the solar wind doesn't affect the Earth in that way? Why have we still got an atmosphere? Well, we have to go deep into the heart of the Earth to understand that. This is a slice through the Earth. At its core, the Earth is very strange, actually, because it's hotter than the surface of the sun. So it's hotter than 6,000 degrees Celsius at the centre. But it's solid, which is odd, because you would think if you heated iron, which is what's sat at the centre of the Earth, up to 6,000 degrees, then it would melt, right? Actually, it's under incredibly high pressure, and that keeps it liquid. That makes it solid, even though it's at an incredibly high temperature, and you might think it'd be a liquid or even a gas. So it has a solid iron core. Outside that, there's this thing called the outer core, which is liquid iron, a molten iron core. And that's the key to understanding how we hold on to our atmosphere. But it's a very interesting bit of maths. It's one of Maxwell's equations called Ampere's law. So you learn at GCSE that if you have a current circulating around, just a moving electric current, you get a magnetic field, right? That's what we think, or we know, is happening inside the Earth. Because there's molten iron, you can get electric currents flowing, and that generates the magnetic field of the Earth. But this is actually the most advanced and precise equation you can write down that says that. This is a magnetic field, and it tells you exactly how that magnetic field looks when you circulate a current, which is this bit. So that just says electric current equals magnetic fields. That bit actually says also change in electric fields make magnetic fields, and I'm going to mention that a little bit later on. But basically, that says a current makes a magnetic field. That's what we think is happening inside the Earth. You get currents flowing, and that generates this force field, a magnetic field.
The Higgs particle, essentially the theory, which was developed in the 1960s for mathematical reasons, basically, was that as the universe expanded and cooled, let's say around a billionth of a second after the Big Bang or so, then empty space ceased to be empty. In more technical language, the lowest energy state of the vacuum of empty space is not to be empty, but to be filled with something. And that thing is called the Higgs field, or if you like, Higgs particles. And so when the golden rule in physics is that everything likes to be in the lowest energy state it can be. So if you want to describe how a ball ends up at the bottom of a valley, you would say it has less energy at the bottom of the valley than it does at the top. So it'll roll down to the bottom. In the same way, the Higgs field was postulated to have behaved in this way. So as the universe cooled down, something happened. It went through what's called a phase transition. It's like water vapor turning into ice on a cold window. The universe went through one of these transitions. The empty space becomes full of the Higgs field or Higgs particles. And then other particles interact with that stuff that sits in empty space. And in that interaction, they acquire mass. So the answer to the question at the most fundamental level, why do you have mass? So let's say why do the electrons in your atoms, why are they massive? The answer is because they're interacting with the Higgs field, which appeared at some point after the Big Bang. That turns out to be correct. We discovered the Higgs particles at the Large Hadron Collider. We don't know precisely how that mechanism worked. That's why the LHC switches on again. This week, I think, if all goes well, or next week, because we need to investigate this thing we've discovered. But broadly speaking, that outline that I gave you is right now, we know. So that's a terrific shift in our understanding. We're talking about the structure of empty space itself.
And this is the aurora australis, the southern lights. So this is the southern pole of the Earth. What happens to the solar wind is that when it hits the Earth, it hits the magnetic field. And because the solar wind is made of electrically charged particles, it's deflected around the Earth. But that's not all that happens, because the Earth absorbs energy from the solar wind in those collisions, and the magnetic field gets stretched out behind the Earth. So literally, on the dark side of the Earth, pointing away from the sun, you get like an elastic band of magnetic field. And you can't carry on stretching that forever. And so at some point it snaps back and accelerates those charged particles to the poles of the Earth, down the magnetic field lines. And you get a beautiful glowing light, because those atoms of oxygen and nitrogen in the Earth's atmosphere are literally shaken. Light is shaken out of them. That's one way of thinking about it, by this snapping back of the Earth's magnetic field. And you get beautiful displays like this. Here's another one, which I think is absolutely wonderful. It's a movie taken from space, again, over the south pole of the Earth. And you can see that circuit of aurora, the glowing atoms of the Earth's atmosphere, excited by all that power initially from the sun, driven into the magnetic field, and then snapping back again. That's a visible illustration of our protection. And I think it's all the more beautiful when you remember that without that, our atmosphere would most likely have been blown off into space and we wouldn't exist. And it's not only the Earth. This is a picture, 3 pictures of the planet Saturn, taken from the Hubble Space Telescope over 6 nights, 24th of Jan, 26th of Jan, 28th of Jan, in 2004. And you can see the aurora over the south pole of Saturn changing as you go from night to night. And that, again, is due to the fact that Saturn has a magnetic field generated, we think, just like the Earth.
One is that we know that about 95% of the universe, of the energy in the universe, is in a form that is not the particles out of which we are made. not the Higgs particles, it's something else. And we call these something else's dark matter and dark energy. Dark energy is something that's causing the universe to accelerate in its expansion at the moment, which is a recent discovery made in the 1990s. The nature of that is unknown. It also turns out that there's 5 times as much matter in the form of dark matter as there is in the form of the matter out of which we are made, and the stars and planets and galaxies that we can see are made. And we don't know what that is either, although it's possible that we can detect new particles at the LHC, which will explain that. So there's an interesting mix now, a sort of a challenge in our understanding of fundamental physics, which is that we have 95% of the universe that looks like it's there, but in some form that we don't understand. We have this thing called the Higgs particle, which looks a bit like perhaps some of the things that might be causing the universe to accelerate, and other speculative stuff. We also have theories about what happened before the Big Bang, so-called inflationary cosmology, which again the data points in the direction that something happened before the Big Bang, and in stopping caused the Big Bang to happen. What's that? So we're at an interesting point where the data is telling us that our theories are inadequate to explain the large-scale structure of the universe.
This is another picture taken from Cassini a couple of months ago now. That's Saturn, which is actually in the background of this picture, and that's the moon Enceladus. Now, if you watched Wonders of the Solar System, you would have seen this amazing moon Enceladus, which is about as big as Britain, but has fountains of ice rising up from its surface. We discovered that there is probably liquid water on this tiny moon powering these fountains of ice out into space. That's Enceladus, and you can just see at the bottom these misty plumes rising up from the surface. These are the ice fountains of Enceladus, taken in this beautiful picture. And then Cassini flew very close, this is after we made the TV series, flew very close below the limb of Enceladus and flew through those fountains of ice. And there it is. So that's the limb of this tiny moon, 1 billion kilometres away from the Earth. Absolutely stunning picture.